So thank you for coming. Thank you for joining this new edition of the MoD Lecture series. Good afternoon. For me, it's a great pleasure to introduce today Paolo Zunino from Politecnico di Milano, the MoD laboratory that you certainly all know. Paolo got a diploma in aeronautical engineering in Milano. And then he moved to EPFL in Lausanne, where he got a PhD on the chair of Alfio Quarteroni, that you also know, because he was one of the first speakers in this lecture series. He moved back later to Politecnico Milano, which is now a professor. You can go a look to his web and see what are his broad range of interest in computational mathematics, computational engineering. More recently, as many others, he got interested on how machine learning can help the big challenges of computational math and engineering, where the classical tools, maybe of numerical analysis, don't get us up to the end. So how can you enhance the effectiveness of our modeling and computational capabilities by machine learning tools? And I had the opportunity to listen to Paolo maybe a couple of years ago, and I was very impressed because he seems to me to be one of the very few that understands the whole process, right? The mechanics, the engineering aspect, the numerics, and also the machine learning. And he was kind enough to accept our invitation to visit us to deliver this talk, in which we will precisely, I think, in a context like ours, in a dissemination manner, try to present his experience and his views on this rapidly evolving field. Thank you, Paolo.
Thank you very much. Thank you very much, first of all, and let me start saying that for me it's really an honor to be here at the Research Center for Mathematics of Data. I think the concept of the center is very timely and important in this moment for math and for applied math. And also, it's a real honor to be a guest of Professor Zuato. So today I will present some topics about the interaction of computational mechanics and machine learning. And I shared this work with brilliant colleagues, senior postdoc Nicola Franco, assistant professor Stefania Fresca, professor Andrea Manzoni, and junior postdoc Piermario Vitullo, who worked with me in, let's say, developing some of the results that we present. Okay, so let me start with a sort of review of some kind of synthesis of the current challenges or current, let's say, structure of computational science and engineering, which is a continuously expanding field of application of computational science to engineering fields. So at the beginning and at the core of this science, there are the approximation methods in space and time, for example, ordinary partial differential equations and numerical methods for the approximation of them. And in the, let's say, about 50 years ago, that was it. That was the essence of computational science and engineering. But today, this is much broader, in the sense that this core is now, let's say, empowered by many other type of technologies, primarily modern order reduction, which are today boosted by scientific machine learning, which in turn enables other abilities, for example, multivariate analysis, and even more, for example, uncertainty quantification, optimization methods that become very efficient solution of inverse problems. And this gives to the original core much more power to attack applied science problems. But even more, there is even an outermost loop, which today is about the integration of, let's say, models and data, which is so important, for example, in the, let's say, creation of this system, which are named the digital twin, is essentially a kind of sort of intelligent system that can constantly learn from data and become more fit and less predicting some scenarios. In the end, the ultimate goal of all this is to enable to take decisions on the basis of some computation, some quantification of some physical effects. And we can only take decision if we really go through the whole loop, because just a numerical simulation is not enough really to decide about the safety of a dam or a bridge or the performance of a complex system such as even a car. So this is the scenario, and basically the topic that I would like to present is how today scientific machine learning is really boosting, empowering new ways of model order reduction, which is basically the technology that, let's say, enable to accelerate the computations based on numerical methods. Okay. So let me now elaborate a little bit more on model reduction and model order reduction and scientific machine learning and deep learning. So on the right, you see on the left, sorry, we see some let's say basic families of reduced order models. There are data fit models, essentially response functions, which are very basic in some sense. On the other hand, there are hierarchical models where one can, for example, use some asymptotic expansion of an operator, and truncated this expansion can reduce the complexity of the problem at the basis of the mathematical structure. And in the middle, there are the projection-based models that in the engineering application are the most popular ones, most also successful ones. And projection-based models are essentially say based on the idea that you take a problem, a discrete problem formulated in a very high-dimensional space, which is accurate enough to describe all the physics about our problem, and then you want to project this representation of the problem in a very high-dimensional space into a lower-dimensional space that, for example, is represented by the most fundamental modes of this type of operator. And this is typically characterized by two possible limitations. On one end, this, let's say, subspace where we project our original problem is typically made by a superposition of both, so it's typically a linear subspace. And on the other hand, sometimes this method suffers of what is named intrusiveness. What does it mean? It means that typically this reduced order model can be separated in two main phases. There is an offline phase where we have to really spend a lot of computational work in order to calculate, for example, how to represent our, let's say, reduced subspace as a collection of nodes, for example, solving an eigen problem. And then you would like to maintain this projection step. If the, let's say, operator that you would like to approximate is a parameterized operator and this parameterization is defined, then we can decompose this operator into parts that are independent of the parameters, and then we can project each of them on the reduced space without any effort. But in some cases, this defined composition is not available, and so we have to really assemble, really construct the high-dimensional problem and then take the whole projection of that, which is actually very costly. So intrusiveness is the limitation in the efficiency of these projection-based models. And so the main message is that today, through the use of basically deep neural networks and corresponding learning algorithms, we can overcome both of these limitations. For example, we can overcome intrusiveness by, let's say, circumventing this projection step and surrogating it through the action of a neural network. But most importantly, we can, let's say, overcome the limitation of linearity by really enabling nonlinear dimensionality reduction through the mappings that we can represent by neural networks. And these are basically the 2 points that I will discuss today. So in order to understand really this type of technology, I think it's fundamental to introduce the concept of Kolmogorov-Henry, which is basically given a manifold S is the distance of the closest linear approximation space of dimension n to the manifold S. So in reduced order modeling, let's say it's extremely important to consider those problems where the decay of the Kolmogorov-Henry with the parameter n is fast enough, which means that this projection-based model will be computationally very effective. However, in the other case, like for example, linear dynamics, multi-scale phenomena, or even the simplest transport-dominated problem, this Kolmogorov-Penwick decays very slowly. Imagine just the propagation of a wave. In order to capture this whole, let's say, propagation with a fixed number of basis functions, we have to collocate basis function in every possible, let's say, point where this wave goes through, which essentially increases the size of this linear manifold that we use for the approximation of the problem. Even though with one, let's say, nonlinear transformation, we would just need one mode. So this is the situation where somehow the classical projection-based methods fail, and this is the situation where maybe the transition to nonlinear approximation is essential. Indeed, there is an extension of this concept of Kolmogorov-Penwick to nonlinear transformations, which basically reproduce the same definition but using general matrix. So the nonlinear Kolmogorov-Penwick would be the distance of the manifold S from all possible functions that are represented by contracting the, let's say, function of the manifold S with a matrix that, let's say, maps them into a lower dimensional set of variables, and then the correspondence inverse or transpose operation that maps this latent space to an original, let's say, high-dimensional space. And so the essential point of transitioning from linear to nonlinear is that, for example, for any set of a certain topological dimension S, there exists a minimal latent dimension, basically an integer, such that the nonlinear Kolmogorov-Penwick is exactly zero. So there is no more representation error in representing the manifold with nonlinear matrix. And this is essential because we aim, indeed, in the model order reduction based on neural network to reproduce this situation with the representation power of, indeed, the neural network. So the essence is that the ability to train high-dimensional neural network really enables to, let's say, achieve the objective of representing a general manifold with almost no error, but with a much fewer number of dimensions. And that's really the point of, let's say, nonlinear model order reduction. So let me now set a little bit the problem. All right. So what we would like to do is really to consider a family of parameterized partial differential equations. So in the sense to be able to solve this equation with, we would like to do that in indeed satisfying certain criteria that we fix a priori. First of all, we would like to develop methods that are completely non-intrusive. So the phase where we collect the data and the phase where we use the actual reducible model are completely separate. On the other hand, we are based on a data-driven approach. This is not the only choice, but it's basically the choice of this kind of methods. And as a consequence of that, it will be essentially based on supervised learning. And finally, we want to be able to apply that in the case of very high-dimensional data. Of course, this is not the only possible pathway. There is a whole, let's say, alternative literature about, let's say, performing basically the same task, where the actual information of the model is not in the data, but is in the, let's say, functional that we minimize, basically in the loss function. So, and these are named the very well-known physics-informed neural network approach for solving PDEs. This is not our choice. This is a very successful approach, but I will not comment about that. So, specifically, what we are about to do is to then, let's say, try to approximate the parameter to solution map of a suitable parameterized family of equations through the representation of a deep neural network. So the general setting is that we define an abstract problem where the operator A will be, in the steady case, for example, an elliptic operator like the Laplace operator or a generalization of that, which is suitably parameterized in the operator, in the forcing terms or in the boundary conditions. And then we also assume that we have a reliable full order model, so a very accurate discretization that we can use to collect the data that will be the source for this reduced order models. And so in essence, what we are about to do is to approximate somehow the solution manifold with a neural net. And the solution manifold being a manifold that is described at the discrete level by sampling the parameter space and collecting different solutions. So we attempted to do this in quite a simple way. For example, by let's say taking one of these equations and considering the solution at one single point. So basically, we want to approximate a simple mapping from the parameter space plus the number of space dimensions to R, because R is indeed the set where the actual solution of a scalar problem is defined. It seems to be an easy problem to be approximated in a neural network. We, let's say, naively tried with different types of dense architectures, even quite expressive, because 5 layers and 500 neurons per layer is quite a lot for such a simple problem. But in any time, we saw that the results were completely unsatisfactory. So the very simple message we learned from this is that anyway, it is necessary to exploit the mathematical structure of the problem in order to achieve something in this direction. And indeed, let's say the pathway that I will explore is really how to move from linear approximation method, where in essence there is a connection between the parameters and the coefficients of the expansion of the solution in a suitable basis, to somehow some adaptive methods which are, let's say, organized by somehow clustering the parameters in some groups, depending on the particular characteristic of the parameter space, and then associating the expansion in this reduced basis to this type of clusters. This is the typical idea of adaptive methods in, for example, in projection-based, the projection-based approach. And to finally, let's say, achieving a full nonlinearity, where we actually replace the concept of a linear approximation space with a nonlinear trial manifold, which is characterized by a number of unknown to be determined latent variables. And what we do is to try to, let's say, approximate the mapping between the parameters and these latent variables. So let me be more precise. And let's start from the classic left.
So here, for instance, when you say test error, so yeah, you write
yes.
unsatisfactory. You know, nobody's happy with 25% failure.
Yes.
I mean, in some of the, you have a training in aeronautical engineering. So what is the level of precision we expect in? Is what, 99?
Yes. No, that's not. Yes, this is a good question anyway. I would say that in our community, at least in what I see in papers and in what we do, the acceptable error of this type of surrogate model is between 1 and 5% is already decently acceptable. 1% is good. 1%. Yes. 25 is definitely not. Yes.
Yeah, there is plenty of room.
Yes.
From 25.
Yes. Okay. So let me elaborate on how to move through these steps. So the classical projection-based approach is that we take our full-order model, we collect a lot of data, sampling the parameter space, we create this data matrix, and actually what we want to find is a sort of eigenmode decomposition of this data. So through solving an eigenvalue problem or a single value decomposition, we find these modes, and we rank them according to the decreasing order of singular values, for example, and at some point we truncate. In this way, we put into evidence, this is the classical proper orthogonal decomposition approach, a set of basis functions or vectors that allow us to, let's say, transform our original high-dimensional space where the full-order model solution was represented into a lower-dimensional space through the projection through the matrix P transpose, and then we can reconstruct the information by multiplying by the matrix B. So, and this is done for projecting the problem characterized by the operator A, matrix A, at the discrete level into this low-dimensional space, and the reduced order model will actually be the representation A in the low-dimensional space, solving basically the reduced coefficients and then expanding back to the let's say high-dimensional representation. This is, of course, is limited if the affine decomposition is not available, and this is of course limited by linear representation of our, let's say, reduced problem. And so neural network can overcome both limitations. The first one is about intrusiveness, can be attacked with an idea proposed a few years ago with a very successful paper by Professor Yannis Sardan and Stefano Rubiali, who proposed this method that today goes under the name of POD-NN, like neural network approach. So the idea is still to, let's say, do the offline work to calculate a proper orthogonal decomposition basis, just as did before. But what we do is we surrogate the projection step through a neural network that actually learns the dependence from parameters to the representation of the high-dimensional solution in the low-dimensional space. So under the assumption that the parameter space of dimension P and the number of, let's say, modes, the number of reduced spaces of number of dimension n is small enough, then we can actually train a neural network, a dense neural network, that through a supervised learning approach, minimize the functional that, let's say, represent the mean square error between the representation of the high-dimensional solution in the low-dimensional space, obtained by projection of all the solutions that we have collected to compute the proper orthogonal decomposition and projected into the low-dimensional space through the matrix V transposed, and the representation of that same reduced coefficient by the neural network. So this is an actually simple, let's say, problem that can be, let's say, successfully solved by training. And this actually enables us to define a direct pipeline from the parameters of our problem to the representation of this solution corresponding to the parameters in the low-dimensional space, and finally the, let's say, reconstruction of this reduced coefficient to the high-dimensional representation of the solution. So this is very effective because it's completely non-intrusive. Once you know your data to calculate the POD, you're done, and this data are never, let's say, touched or again, and there is no knowledge to know afterwards the definition of the high-dimensional operator. Everything at the, let's say, reduced order model level works with in the setting of the low-dimensional configuration. So non-intrusiveness is completely, let's say, solved by this very simple but effective idea. But moving on.
So what do you mean by intrusiveness here, or non-intrusiveness?
Intrusiveness is when you have to, let's say, exploit information about the high-dimensional formulation of the problem, the full-order model, into the operation of the reduced order model. So, for example, if you have, if you want to evaluate the reduced order model for a new parameter in the classical setting without any special assumption, you have to take your full-order model operator and project it onto the reduced space, which means that you have to access this operator in high dimension, which is a cost. Even though you don't have to solve the system, right? The yellow system which is high dimensional, you have to assemble the operator, which is sometimes costly, sometimes not even accessible. For example, if you use a commercial code, you don't have access to the matrix, you just have access to solutions. So intrusiveness is about this. Non-intrusiveness is when you just rely on the output of your code. No access to what is inside, in some very basic practical sense. So the next step is about solving, let's say, the linearity, let's say, limitation. And this can be done by somehow generalizing this operation of dimensionality reduction through the, let's say, matrix, the reduced basis matrix V, through a structure that is well known in machine learning, that is named the autoencoder. And the autoencoder is basically a representation of two mappings that start in the high-dimensional configuration of data, and through the mapping psi prime, contract them into a low-dimensional representation, and then for the mapping psi, expand this, let's say, compressed information into the same formulation of the image, into the same representation of the image. So the autoencoder is a structure that performs nonlinear dimensionality reduction and can be actually trained in an unsupervised way, basically feeding this, let's say, construction by data that are basically solutions of our discrete operator at different parameter points, and it can be trained by minimizing the representation error. Right? So we don't have to know what is the corresponding parameter that generated that data. Next, and this autoencoder actually implements the nonlinear dimensionality reduction that we needed and identifies a latent space that represents our solution with a much lower number of degrees of freedom through a nonlinear transformation. And afterwards, once the autoencoder has been trained, we can now use the tools developed by the PODNN approach and, let's say, somehow train a similar network C that, let's say, approximates the parameter to latent space representation of the solution mapping, and disconnect the encoder, and finally obtain a similar structure as before that for any value of the parameter provides a representation of the corresponding solution in the latent space, and finally decode this information into the high dimensional space where we want to represent our discrete solution of this operator. So this is entirely non-intrusive again. This is also entirely based on nonlinear transformation. So basically, it let's say represents our high-dimensional problem into a low-dimensional nonlinear trial nonsense, and is based on the combination of basically three neural networks: the encoder, the decoder, and the parameter to latent space mapping. And this idea has been originally proposed, at least in our context, by Fresca de Manzoni, and then we collaborated with Manzoni and Franco to consolidate this idea and also make some analysis that I will present in a minute. Just to show some results, here we have a classical aggression fusion problem in two dimensions, where we have introduced a parameterization with 7 parameters for diffusion in these small circles. The angle of the advective field denoted by the arrow, and the location of a concentrated source. All these characteristics are typical to, let's say, slow down the convergence of the linear Kolmogorov n width, and to make this problem hard to solve with classical linear projection methods. And we see here the, let's say, results, a visual comparison of the results by this DL-ROM approach based on nonlinear approximation. And we see that visually, but also quantitatively, in terms of mean square error, the error is quite satisfactory, almost 1%, as I was mentioning. To train this system, we have to collect about 10,000 different solutions, 10,000 data, which is a lot. But if you think that this problem is parameterized in a 7-dimensional parameter space, 10,000 points is about 3 to 4 points per dimension, which is not huge in practice. So this is actually performing quite well. Another idea is can be used, similarly, to construct not an approximation of solutions, but an approximation of continuously varying, let's say, basis function. So we have a basis function which is still a linear approximation space, but that continuously adapt to the parameter. So basically generalizing this idea of clustering the parameter first and then computing basis function for each cluster. Here we have a completely continuous, let's say, variation of the basis, which makes it completely adaptive. So the idea was still to, let's say, leverage on this neural network that approximate the dependence from parameter to representation into a latent space, and then to, let's say, connect to the actual latent space different kind of root networks, which in essence are different decoders that actually each computes a basis function. When we collect this basis function, we orthogonalize them into a proper projection matrix. And the whole system can be trained by minimizing the representation error of the actual true discrete solution with the, let's say, projection into this adaptive basis set. And this is actually working quite effectively to really, let's say, minimize the number of dimensions, the number of bases that we need for constructing a linear approximation. Here, for example, we have a case where the parameters are the positions and, let's say, angles of this obstacle in a, for example, in a Stokes flow. And what we see is that, for example, with just a handful of these adaptive bases, for example, 2 or 3, we can achieve the same projection error that we would obtain with more than 10 times classical proper orthogonal decomposition basis. It is fixed over the whole parameter space. And this performance is even better than the classical nonlinear, let's say, approximation that we can obtain through an autoencoder. So this is quite effective if you want to still use the sort of interpretability of a linear projection method, but with a set of basis functions that continuously adapt to the parameters, which can be also combined with a similar approach that actually takes care of the behavior of other parameters that have a more smooth, let's say, influence on the solution. So let me come to a second part of this talk where we actually asked some questions about the properties of this actual approach, starting from the fundamental question of how to choose this latent dimension that we, where we approximate the, let's say, when we approximate our high-dimensional solutions. This is a number that should be fixed a priori by designing the architecture of these autoencoders. What are the errors that we can expect from this type of approximation? And finally, what are the guidelines to design this technique? Can we develop some, let's say, mathematically sound rules to, let's say, design these autoencoders and other approximation type of networks? And finally, how do we approximate more general problems? This was applied into very simple tensor crowded domain. Can we generalize to any shape of the domain? And also, lastly, a very important and hot question, how can we extend this to time-dependent? So let me start with the first question that is addressed by some classical topology and embedding theorems. So in the specific case of partial differential equations, for example, in divergence form with a suitable, let's say, coefficient that can be generally, let's say, parameterized, we can prove that if the parameter the dependence of the coefficients to the parameters is smooth enough, just Lipschitz, then the minimal latent dimension of the solution manifold of this problem, basically the dimension of this, let's say, latent space that ensures a nonlinear Kolmogorov width equal to 0 is not larger than 2p plus 1, where p is the topological dimension of the solution manifold, which is essentially the number of parameters. Okay, so if we take this problem with p parameters, we know that with at most 2p plus 1 parameters, there will be no representation error. Yes. And more, if also the parameter to solution map is bijective, then this minimal latent dimension becomes equal to the topological dimension of the solution manifold, basically equal to p. So by p latent variables, we can basically reproduce the entire solution map. Okay? This result can be also, let's say, a little bit extended in the context of stochastic differential equation, or more precisely, partial differential equation with stochastic coefficients, where we have, for example, a diffusion equation with a stochastic diffusion field, diffusion tensor, and of course we want to let's say, make calculations to represent this stochastic field as a combination of modes, and we want to truncate this expansion to, for example, to the order p, which in essence is the number of parameters. Okay? And so we know that if we take the minimum data dimension equal to or larger to 2p plus 1, what we can prove is the expected value of the error, of the representation error, is only dominated by the truncation error of the Karune-Loew's function of the random field, but there is no role of the representation error of the autoencoder. So in essence, there is, again, the representation error due to the autoencoder approximation is could be, let's say, sent to zero. So in essence, the message is that these techniques provide a very efficient way to perform dimensionality reduction. The next step is to make some discussion about the error. So first of all, it's useful to remind that the error of, let's say, representation of data through a neural network can be decomposed decomposed by the, let's say, additive composition of different sources of error. First of all, the generalization error, which is basically the error that we make by replacing our error functional integrated over the whole data set into the empirical error that is just sampled in a finite number of points of this data set. Then there is the optimization error that is due to the fact that we never converge to the absolute minimum of our functional, but typically the convergence history is truncated at some point in the neighborhood of some local minimum. And finally, there is the approximation error made by the fact that at the continuous level, our encoder and decoder mappings are just general continuous mapping or regular mappings, but we represent them with a neural network, so there is obviously an approximation error that appears. And we were able to analyze, or we focused on just on the last component, trying to answer the question as follows. Given a suitable tolerance, epsilon, how big we should take our deep neural network configuration in order to make sure that we approximate our high fidelity solutions with a tolerance no less than epsilon, no larger than epsilon. So we work in a sort of worst case scenario where we take our supremum over the whole data set of the loss function. The loss function being basically the mean square error between our, let's say, high fidelity solution and the representation through the neural network. And under some, let's say, quite restrictive assumptions, such as that the parameter solution map is Lipschitz, and also that the ideal, let's say, encoder and decoders are, let's say, not only continuous but also regular as time differentiable with bounded derivatives, and also with the assumption that there exists an integer m such that the linear Kolmogorov width of our solution manifold is smaller than the desired tolerance. So typically this integer m is probably very large. Then we can provide some bounds, some explicit bounds of the number of layers and the number of weights that we must use in the configuration of our encoder, decoder, and parameter to solution map, such that this tolerance epsilon is satisfied. And in this bound, that is quite messy, we see that there is an important effect that emerges and has been heavily studied by others, such as the group of Professor Schwab for many different cases. Here is the one paper about elliptic partial differential equations, that the size of these networks that approximate solution of PDEs generally scale as polylogarithmically with respect to the tolerance. And this is quite a good scaling compared to other computational methods. So this is what also the representation power of neural network can actually do in this context. The third question is about more, let's say, practical or more precise guidelines to design our neural networks in this type of configuration. So let me focus here just on the autoencoder structure, which is in charge of dimensionality reduction, really the core of this idea. And I would like to mention first that, let's say, in the case where we handle high-dimensional data, for example, the dimensionality of the number of degrees of freedom of numerical simulation of some engineering problem, this high dimension can be millions, okay, is very useful to put in the periphery of this autoencoder some convolutional layers, which are very effective in handling this very high dimensionality efficiency, and in the core of the autoencoder, typically dense layers, in order to have the maximum of expressivity. And in this type of configuration, we were able to establish some quite, let's say, precise guidelines that link the characteristic of the full order model in terms of, for example, mesh resolution and regularity, and the specific architectures of these layers. For example, we were able to understand and prove that the mesh resolution of our full order model affects the depth of the convolutional block. So the finer the mesh in our, let's say, application, the more convolutional block we have to use at the periphery. The desired accuracy that we want to achieve affects the depth of the dense block. So if you want to be more precise, we have to increase the number of blocks in the core. If the regularity of the solution manifold affects the width of the dense block, while the regularity of the solution space, measured with some Hilbert space, for example, affects the number of channels in the convolutional layers block. So these are quite useful guidelines that were kind of formulated more rigorously as almost as a theorem, which actually helps really to understand how to adapt from this construction from one problem to another. But finally, the limitation that we have so far, especially using convolutional layers in the autoencoder, is that we are limited to very simple domains that have essentially a tensor product structure which mimics the structure of images, right? So where our degrees of freedom of our high fidelity model correspond to pixel in a picture. So this is acceptable, but definitely not acceptable for engineering application. So what we will try to do is to mimic the good properties of the convolutional layers, of the convolutional neural networks, which are basically the ability to, let's say, to be trained with a very few parameters, and also the ability to reproduce a sort of multi-resolution using, let's say, a more general approach that is based on the knowledge that we always have an underlying computational mesh for, let's say, describing our data. It's not just random data, they're based on a geometrical mesh. So what we came out with is the concept of mesh-informed neural network, which are based on the idea that every neuron in a mesh-informed neural layer is related to one point in a computational mesh, okay, one node in a computational mesh. And so starting from, for example, from the representation of our solution in a high fidelity, very, let's say, accurate mesh, we can define a hierarchy of coarser and coarser meshes that enable us to represent those high-dimensional data with lower and lower dimensionalities. And also through the information of the, let's say, positions of nodes into the mesh, we can also introduce some sparsification. Indeed, let me show this concept with a very simple example. Imagine that we have two meshes, a coarse one and a finer one. If you want to represent the, let's say, interaction of the nodes of the coarse one with the finer, we can end up with a 3x6 matrix. But then we can, for example, localize and sparsify, saying that node number 2 in the coarse mesh only sees node number 6, 4, and 2, the neighbors nodes in the finer one. So we actually sparsifying the connections, right? And in the same way, in the corresponding weights of the mesh-informed layer, we're sparsifying the weight matrix. So we have much less weight to train. And this is actually very effective in this specific context. So with the mesh-informed neural network, we were able to train, let's say, networks that are able to handle very high-dimensional data defined on meshes. And this sparsification also improves the, let's say, generalization capabilities of such networks, as we observed experimentally. We have no proof of that. But we tested that on an interesting problem that comes from the propagation of some disease in the brain. We choose that just because the brain has a not simple topology, let's say, and the PDE was a time-dependent nonlinear, let's say, diffusion reaction type of PDE. We see that with the use of mesh-informed neural network instead of the classical dense one, we were able to reduce the error and significantly reduce the memory consumption to represent, to store this information into a code. Moving on, this led us to the idea that using this architecture, we could actually generalize the POD-mean approach, the POD-NN approach to high-dimensional data. So we don't need anymore to have just a handful of parameters. We can handle basically parameters that are represented in an infinite dimensional space, discretized through, for example, a finite element space, and use them in this parameter to solution map. For example, here is a problem that is inspired to microstructure. So basically, we have a PDE with some parameters that can be, let's say, split into families. Classical parameters that are related to the operator, but other microscale parameters that, for example, can describe the configuration of a graph inside the domain, and we assume, for example, that this graph is the support of the forcing curve. Like in a heating system, this could be the heating channel into some medium. This example is actually inspired to our microcirculation, which is essentially our biological heating system or distribution system. So we have now a highly dimensional parameter set that describes any possible configuration of this graph, which can have different number of nodes and edges. So in the end, we, for practical reason, we transformed this high-dimensional parameter space into actually an infinite-dimensional parameter space, where we encode the graph with the distance function of every point in the domain of the nearest edge of the graph. So we have a function, not any more parameters, and we actually discretize that with finite elements. So we end up with a finite but high-dimensional number of parameters. And so we now need to, let's say, reproduce the POD-NN approach, but instead of using a classical dense network for the parameter to reduce space map, we use the mesh-informed network, which totally enables to train this type of system without any troubles. And this is just the, let's say, an example where we have the high fidelity solution of this kind of microstructure problem. And you can see there are small details that are determined by the location of this, let's say, graph and the action of the solution. And we decided to use just 20 proper orthogonal decomposition basis function in order to represent this solution. And we see that these only 20 modes are not enough to capture all the features of the actual high-dimensional solution space. This is expected, as this is a sort of multi-scale problem, which is one of the cases where the classical linear projection problems fail. And indeed, the POD-mean approach couldn't improve that because it still works with a linear approximation space of 20 bases. So the idea was also that we could actually use the capacity to represent, let's say, high-dimensional data with mesh-informed networks to correct the, let's say, this type of solution using the concept of closure, like in turbulence. If you don't get the microscale, you try to add something that, let's say, artificially puts it back. And this closure can be actually learned, for example, by taking the representation of solution in the low-dimensional space, expanding into these 20 modes, but then using another mesh-informed neural network that takes the, let's say, graph-based data and corrects the actual error with the action of a nonlinear, let's say, operator that is represented as a neural network. And this was extremely successful because we actually operate at the level of the high-fidelity finite element space. So we could, with this, let's say, correction, completely capture all the details of the original, let's say, solution affected by the microstructure with a very low computational cost, as shown, for example, a few numbers are shown here. These systems can be trained in a matter of minutes. Of course, this is not the computational cost and the time needed to collect all the data. This is another story. But the training time is not a problem at all. And also, you see the gain between the full order model and the reduced order model is about orders of magnitude. So in all the cases I have experienced, basically this type of technology almost annihilates the computational cost of approximating PDEs. Of course, with a trade-off, now the error that we can afford is no longer, let's say, rocket science, but is, let's say, about 1 of a few percent, but still, in many applications, this is very acceptable. Another, can I go on another 10 minutes? Okay. Another idea is then, okay, what can we do for problems where even the, let's say, full order model is not available because it's too expensive, like the real multi-scale problems. So the classical, let's say, limitation of a genuine multi-scale problems is that we cannot perform a sort of direct simulation, right? Because it or is too expensive, or even the operator doesn't exist in some explicit form. Assume that it's too expensive, just to simplify. The classical idea of multi-scale finite element methods, which is very effective, is to decompose the macro scale of the domain that we would like to solve, this multi-scale operator, into cells, into elements, and then for each local element, we define basically a multi-scale basis function, and then we assemble all these bases and we project our operator into this, programmatic projection into this, let's say, multi-scale basis function that, let's say, actually captures the microscale behavior. And this actually can be reproduced with this type of reduced order models, because actually now we understand that our reduced order model can generalize with respect to the configuration of the microscope. So we can train a reduced order model locally, basically at the level of this subgrid level of the multi-scale FAM, and apply this local reduced order model that are, say, able to capture the microscale effects with a very modest computational cost, and assemble the global solution with classical algorithms, for example, the one provided by domain decomposition theory. So one very basic preliminary idea would be to start from a domain, decomposing in subdomains, and iterate the, let's say, solution in each subdomain. So for example, with a Schwarz iterative method, could be overlapping or non-overlapping, but we replace the actual computation of the solution at the level of subdomains with a reduced order model that is trained only at the level of the subdomain. So we can, for example, let's say, cycle through this algorithm. Let's say, at every iteration, isolate one subdomain, feed the local reduced order model with the configuration of whatever microstructure and the information of the, let's say, values of the neighboring solutions at the interfaces, okay, which anyway are high-dimensional data that we can handle, and then cycle, and then assemble a global solution to some, let's say, operator, in case applying some mutter, and by cycling to the sparse iterative algorithm, we can converge up to some tolerance to the reconstruction of the global solution that we never had the need to access. Okay, so this is quite a simple idea, but I believe that a refinement of that idea could be actually quite effective in the way of multi-scale, deep learning-based reduced order models. And finally, let me come to the last point, where I would like to comment briefly on ongoing research on extension of these methods to time-dependent problems. So the basic idea is that if we have time-dependent functions, we can anyway represent the time evolution of these functions in a latent space. For example, here we see the latent space representation of the evolution in a two-dimensional case of say, translation wave or a kind of, let's say, evolving field. And so the idea comes that actual time-dependent problems can be seen in a way where time is a parameter. Okay? So the classical deep learning-based reduced order model can be actually straightforwardly applied to time. with some obvious limitation that I'm about to talk. So we can take a time-dependent problem, we can solve it and sample it at different time points, collect all this data, perform, for example, let's say train the autoencoder or perform proper orthogonal decomposition, and then train a network that, let's say, learns the time to reduce coefficient mapping. And through this way, we can, let's say, develop a system that for each time gives us an approximation about high fidelity solution. Now this works, but has some serious limitations. The first one is that this method doesn't have any knowledge of the actual time dynamics that were represented in the operator. So this is just about learning data. So, and with the failing in this, obviously this, let's say, methods don't guarantee any time continuity or time stability, and also for this reason they are absolutely unable to extrapolate. We can trust them only in the time interval where we have collected data, and absolutely nowhere else. So the ongoing research by two brilliant groups of colleagues that are listed here, for example, Francesco Regazzoni and Stefano Pagani on one end, and Andrea Mazzoni and Stefania Fresco on the other end, who came with, let's say, basically a common idea. Let's really try to reproduce, to learn the latent dynamics of a high-dimensional system by, let's say, projecting these dynamics to, for example, a system of encoder and decoder into a latent space, and then tracing these dynamics and learning their representation through a neural network, solving that corresponding ordinary differential equation, and then reprojecting back on the high-dimensional space. So it's basically dimensionality reduction with the dynamics at the same time. I will not be, let's say, too long on that, but these ideas are similar, but they differ in the, let's say, type of architectures and type of interpretation. There is the latent dynamic nets, which, let's say, reproduce this idea, leveraging on some concept of a recurrency neural network that is able to learn the dynamic first, and then a representation network that at any point of our domain of interest can, let's say, reconstruct the whole solution starting from the information at the level of the latent dynamics space. And then there is a similar idea, but implemented at the level of the whole domain. So in the case of high dimensional representation of the solution, there is named latent dynamic models, which indeed can be formulated here as a learning problem where we want to minimize an error, that is a representation error of our high-dimensional solution with respect to the, let's say, corresponding representation of the latent space decoded to the mapping psi prime. But this minimization is subject to a constraint, and the constraint is the satisfaction of an ordinary differential equation where the function f has also to be learned. Okay? So we are actually learning the formulation, the function of the dynamics in the latent space, which is not known a priori. And let me conclude by saying that this Villeron method is not just one method, but is actually can be interpreted as a family of methods, where we can, say, design different approaches according to the level of nonlinearity and the level of trainability, leveraging on autoencoders and this mesh-informed structure. So, for example, starting from linear classical projection-based approximation methods, we can introduce the pure DNN technique, and that can be extended to high-dimensional data using the POD min mesh-informed neural network technique. We can further move to a higher level of nonlinearity by using an adaptive set of bases constructed through this deep orthogonal decomposition, which is the generalization of POD, proper orthogonal decomposition with a continuously adaptive basis. And finally, we can also move to the fully nonlinear dimensionality reduction case implemented with autoencoder, where we can combine different type of networks, the convolutional networks or the mesh-informed. And with that, I would like to just say that these methods have been successfully applied in non-trivial applications, such as, for example, the simulation of cardiac propagation of electrical signals in the heart by Fresca, Dede, and Mazzoni, to the simulation of a micro electromechanical device by Fresca and Mazzoni and the co-workers at the Department of Structural Engineering at Politecnico. And in my case, just a final note, just to mention something that Professor Guadua said. In my research, I'm trying to use really effectively these methods in order to, let's say, accelerate and facilitate the workflow of using mathematical models, let's say, up to, let's say, in the context of computational oncology. So basically models about the progression of population of cancer cells and the interaction of this population with the availability of nutrients and metabolites and so on. So basically systems of reaction diffusion, time-dependent partial differential equations. And obviously in this context, first of all, one simulation doesn't mean anything. We have to really test these models in many types of scenarios. And in this case, the ability to perform a sensitivity analysis, uncertainty quantification easily through the action of the use of the models is extremely important. And here we have the work of my, let's say, PhD students and postdoc, Mario Vitullo, who did exceptionally well in this area. And finally, this is somehow enabling all the so-called digital twin technology, which is in many areas, including biology, is becoming very important. And with that, I would like to conclude and say that we are actually hiring a few postdocs in this area. So if anybody in the audience or if anybody knows people who are interested in exploring this exciting field, please let me know. And thank you very much for your attention.